So in chapter 6.1, we're going to be starting confidence intervals for the population mean. So for this section, we're going to have sigma, we're going to have the population standard deviation. So what we're going to be doing, we're going to have the mean of a sample, the standard deviation of the population, and we're going to be given a certain confidence level. And what we will be doing is we're going to create an interval that the population mean falls within with that certain amount of confidence. So essentially we are making this estimation for the population mean given a sample, standard deviation of the population, and a certain amount of confidence, which is going to be a percent. So before we do that, I have to mention several other things. So the confidence level, or the level of confidence, we're going to denote with a C. It is the probability that the interval contains the population mean. And what this is in terms of the standard normal curve or the normal curve, it's going to be the area under the normal curve between a negative z value and a positive z value. We're going to call these critical values and denote those negative z sub c and positive z sub c. So we could create a little graph down here. So this is the standard normal curve, and we have our two critical values, negative z and positive z. They're the same number, but one's negative, one's positive. So this means that the area between them is going to equal that confidence level C. Okay, so this is the probability that this interval will contain the population mean, mu. Okay, so recall the central limit theorem version of finding a z-score. We have z equals x bar minus mu sub x bar divided by sigma over the square root of n. So instead of z, we're just using z sub c for just the notation for the critical value. And what we can do here is we can actually solve for that numerator. We can solve for x bar minus mu sub x bar by multiplying both sides by the denominator. So if we do that, we multiply both sides by sigma over the square root of n, so it multiplies to the other side and multiplies the z. So this side of the equation, the left side, is the difference between the sample mean and the population mean. So what this is called is the margin of error. We denote it with an E. So the margin of error is going to be z sub c times sigma over the square root of n. So we are determining how close the sample mean x bar is to mu, which is the population mean, with a certain level of confidence, which is the c value, and we're going to use that c value to find that z-score z sub c. Okay, so the reason why I wrote mu on the right here instead of mu sub x bar is because if we remember, mu sub x bar equals mu. So that was from a couple sections ago. So a couple conditions have to be satisfied in order for this to work, in order for this to be relatively or pretty accurate. The sample has to be random, hopefully that's pretty obvious, and either the population itself has to be normally distributed, or the sample size has to be greater than or equal to 30. Okay, so let's do an example using that margin of error. So we want to find the margin of error for the population mean using a 95% confidence level, given that sigma is 7.9 and n is equal to 40. Sample size is equal to 40. Okay, so we know that we're using this formula, which is E, the margin of error, which is the difference between the sample mean and the population mean. It's going to equal z times sigma over the square root of n. Okay, so we are given sigma and we are given n. So we have to find z using the 95% confidence level, which is 0.95 as an area. So we can set this up on the table to see how or the graph, to see how we do this. So it's going to be negative z and positive z. So a 95% confidence level is going to be 0.95 of the area underneath the curve is going to be between negative z and positive z. So we need to figure out what the z-score is. So to do this, if we remember we've done this before, we need to, in order to use the table, we need to relate this to an area to the left because that's what the table tells us. So if 95% of the area is between two values, that means 5% is on the outside, right? So 5% would take up this side and this side. Since this is symmetric, that means we have 2.5% here and 2.5% over here. So as a decimal, 2.5% will be 0.025. So that's going to be the area in these little non-filled in, non-shaded in portion. So what we can do is we can find the z-score for an area to the left of 0.025. So what this means is we have to look up an area, so we have to go inside the table and find 0.025. We have to find the z-score that corresponds to this. When we look this up in a table, we will end up getting a z-score of negative 1.96. Okay, so let's just make sure we still know how to do that. So finding an area of 0.025, that's going to be right about here. There it is, 0.025. So the z-score for that is negative 1.96. So that is our negative one. So the one that we found on the table was this right here, that z-score. So the one that we're going to be using is going to be positive. So it's always going to be the positive one that we're using. So it's going to be z sub c equals positive 1.96. So I'll make a little note, always use the positive version. Okay, so that's our z that we're plugging in now. So going back up here, going to the margin of error formula, we have E equals z, which is 1.96, times sigma, which is given to us 7.9 over the square root of n, which is 40, which is given to us. So we plug this in the calculator, and I think I rounded a little bit, but I have 2.4. So what this means is that we're 95% confident that the margin of error, meaning the difference between the sample mean and the population mean, is 2.4. Okay, and then what that means is that we are 95% confident that the population mean is within 2.4 units of the sample mean. Okay, so we don't have the sample mean for this one, so now we're going to be moving on to problems where we have the sample mean and we can actually construct an actual interval that the population mean will lie within. Okay, so just like I said, for confidence intervals for the population mean, so once again, we're given sigma here. The population standard deviation is known. That's important because in the next section, it's not going to be known. So we're going to be doing it a little bit differently in the next section. So we're going to be determining how confident we are that the population mean falls within two numbers. So the way that we do this is we say a C-level confidence interval for a population mean is going to be x bar minus e for the lower bound and x bar plus e for the upper bound. So what this gets read at, how this gets read right here in the middle is that the population mean is between x bar minus e and x bar plus e with a certain level of confidence. So we're going to do pretty much what we just did. We're going to solve for e, which is the margin of error, and we're going to be given x bar, which is the sample mean, or we might have to calculate the sample mean given a sample data set. So the general steps here for constructing a confidence interval, we're going to verify that sigma is known, because that means we use the z distribution, and that the population is normal or n is greater than or equal to 30. we're going to find the sample size n and the sample mean x bar. Those steps should be pretty easy. Step 3, that's the one where we have to find the critical value, that z-score z, that corresponds to the confidence level that's given. And then we have to find the margin of error, just like we did. And then we have to form this confidence interval by subtracting e from the sample mean and then adding e to the sample mean. Okay, so let's do a couple examples here. So we want to construct a 95% confidence interval for the population mean, given that the sample mean is 29.6, the sample size is 40, and the population standard deviation is 7.9. So first, we have to verify a couple things here. We have the population standard deviation is known, so we know that we're doing this method here. And we have the sample size is 40, which is greater than or equal to 30, so we're good with that one also, so we're good to go. And we are also given n, and we're given sigma. So moving on to finding the critical value z. So I'm just going to write down the formula here. Our main goal that we're going to be setting up is going to be x minus e, x bar minus e for the lower bound, and x bar plus e. And this is where e is z times sigma over the square root of n. Okay, so all we have to do is find the z now. So finding the z for the 95% confidence level. So we actually just did this in the last one. We found the z for 95% confidence. So that was the area between these two values, negative z and positive z, is 0.95. And we said that the z value was 1.96. So that was just from the previous page. We already did it, so I'm not going to show any work here. And we can plug in these values now into e. So these are actually the same exact numbers as before. So it's going to be e equals 1.96 times 7.9 over the square root of 40. Same numbers as last time. We got, right over here, we got e equals 2.4. Okay, so now going back up here to our original setup, it's going to be x bar minus e. X bar is 29.6, minus e is 2.4, and the population mean is between that value and 29.6 plus 2.4. So all we have to do is subtract those and add those, and we get the population mean is between 27.2 and 32 with 95% confidence. So you want to make sure that you are putting the little conclusion saying 95% confident that the population mean lies within that interval. Okay, so just kind of a quick little recap for what we just did. We had a sample of size 40. We took the mean of the sample and got 29.6, and somehow we have the population standard deviation. So we're saying that the population mean is between 27.2 and 32 with 95% confidence. Okay, so let's do one more here. So we want to construct a 99% confidence interval for the population mean given this following data set. And we want to assume the population standard deviation is 4.3 and that the population is normally distributed. So a couple quick checks to make sure that we can do this. We have sigmas given to us, so that's known. And our sample size here is not over 30, I don't think. If you count all these up, I don't think that's over 30. However, it does say that the population is normally distributed, so that satisfies that requirement. So it's normally distributed, meaning it's normal, so we are good to go. So setting up what we want here, we're going to set up this confidence interval. It's going to be x bar minus e, and x bar plus e, so mu is between both of those. So we do not have x bar this time. X bar is going to have to be solved for. We're going to have to take the mean of that data set. So we're going to have to add up all of those values and divide by how many there are. So I'm just going to do that right over here. I'm just going to write x bar equals the sum of those data entries divided by how many there are. So that's going to be the sum divided by, I think there's 20 of them. So if we add all of those numbers up and divide by 20, we should end up getting 24.1. So I'll put a little arrow saying that's the mean of that data set right there. Okay, so now it's pretty much just like that same question that we had. So we have x bar for our interval. We need to find e. So finding e, it's going to be that same setup. It's going to be the margin of error is z times sigma over the square root of n. And once again, we're given sigma, and n is the number of data entries, and there are 20 data entries up there. I'm just going to write that down here. We have sigma is given to us in the problem. Sigma is 4.3. N is the number of data entries, which was 20. And we need that z value. Okay, so we find that z value based on the confidence level, which was 99%. So it's 99% confidence level. So what that means is we're going to find the z-score such that 99% of the area falls between negative z and positive z. All right, so once again, we want to relate this to an area to the left because the table tells us areas to the left. So if 99% of the area is between those two values, that means 1% is outside of them, which means 0.5% is here and 0.5% is here. So as a decimal, 0.5% would be 0.005. So what we're going to do is we're going to look up that in the table again, 0.005. And we have to remember that when we find this value in the table, it's going to be negative, and we're just going to use the positive version of it. Okay, so looking for this value in the table, 0.005. So 0.005 is going to be about right here. So it is exactly between 0.0051 and 0.0049. So remember, you can think of those as like 51 and 49. Our value would be 50. It's exactly between them. So that means we're going to take the average of their two z-scores. So we're taking the average of negative 2.57 and negative 2.58. So when we take the average of that, we would add them up, divide by 2, or the shortcut is going to be that all you have to do is go to the smaller number and throw a 5 in the thousandth place. So that means the z-score for our value is going to be negative 2.575. Okay, so that's going to be z sub c, or the z value, sorry, the z value that we found was negative 2.575. But remember, we always use the positive version, so z sub c is going to be positive 2.575. Okay, so plugging this in, finding that margin of error. Once we have this, that's pretty much the hard part. So it's going to be 2.575 times 4.3 over the square root of 20. So plugging this in the calculator, we should end up getting about 2.48. Okay, so that is the margin of error. So that's the hard part here. So now we have to go back up to what we are starting to do. We're looking for this confidence interval, x bar minus e and x bar plus e for the endpoints. So the x bar that we found was 24.1 minus e, which was 2.48. And the population mean is going to be between that and 24 plus 0.1 plus 2.48. So we subtract those and we add those, we're going to get 21.62 on the left. So mu is greater than that, and it is less than 26.58. And there is our margin of error. So what this means is that we are 99% confident that the population mean falls within this interval. So our original sample mean of the sample was 24.1. So, which should make sense here because that lies within this interval. So our original sample mean was 24.1, and we said our population mean falls between 21.62 and 26.58 with 99% confidence. So in general here, as the confidence level goes up, so the higher the confidence level, the wider the confidence interval will be. The lower the confidence level, the more narrow or close together the confidence interval will be. Okay, so that's it for chapter 6.1. We are just making assumptions about the population mean, coming up with an interval that it lies within, given the sample mean and the population standard deviation. So this was done using the z-table and the z-distribution. For the next section, we're also going to be doing confidence intervals, but we're going to be doing it when the sample standard deviation is given, not the population standard deviation. That will not be the z-distribution anymore. That will be the t-distribution. We'll be using a new table. So we'll be doing it slightly differently, but it's going to be the same concept. And there will be a shortcut to find the critical value z on the t-table. So this whole thing right here, that whole messy thing that we did, finding that z value, there's going to be an easier way to do it. For the z value, there's going to be a hidden z value on the t table, but we'll mention that when we get to the t table. Okay, so that's it for this section.